TPM-based focused breakdown reduction strategy in industry. Abstract current trends in many industries is to shift from traditional maintenance methods to implementing total productive maintenance. TPM its ultimate goal is to increase reliability and availability, and the way to accomplish it is through elimination of major losses, resulting from mechanical nature that are visualized by the overall equipment effectiveness, OEE, tree. The main key performance indicators for this research are, OEE, mean time before failure, MTBF, mean time to repair, MTTR, and breakdown percentage. Therefore, this paper provides a review of the available approaches for lean TPM implementation in industry, with specific emphasis on breakdown reduction. The gains in productivity or effectiveness were achieved only through measures in TPM, mainly the preventive maintenance, PM, pillar, and not harder labor. The approaches used in achieving these goals included, autonomous maintenance, continuous improvement, root cause analysis for failure, preventive maintenance among others. Keywords: total productive maintenance, overall equipment effectiveness, breakdown reduction, mean time before failure. Introduction. For decades, industrial and other organizations concentrated most of their attention on production, generally ignoring the maintenance function. Recently there has been a gradual attitude change in how general corporate managers view the maintenance function. Peterson, 2013. One of the most important factors forcing this change was that maintenance departments became major cost centers within the organizations. Today, with general operating costs rising at the rate of 10% each year, there is the potential for the realization of significant savings in the maintenance department that deserve serious scrutiny. Bruce, 2011. Lean manufacturing is an approach in manufacturing that aims to improve product quality and output, reduce costs, and eliminate all possible waste. This is achieved through total productive maintenance, TPM. Early automobile manufacturing had sparked the creation of lean manufacturing. John Krafcik and Taiki Ono had combined the necessary criteria in order to create the Toyota Production System, TPS. This combination includes the skill and knowledge with the standardization of the work involved in TPS. Efficiency of the moving assembly line was also emphasized, including the concept of teamwork. Womack et al., 1990. The term lean production system was introduced by John Krafcik in 1998 in his review of the TPS, while Womack et al., 1990, had popularized the term of lean manufacturing. Regularly, lean manufacturing is always related with benefits such as increased quality, reduced inventories, increased customer satisfaction, increased flexibility, and reduced manufacturing times. Womack and Jones, 1996, Ross and Francis, 2003, Alavi, 2003. It is difficult to convince the managers and employees to think and act in a different way. It is also difficult to manage external relationships with the suppliers and customers. Customers may be unable to place predictable orders, causing the organization fail in preparing the inventory to meet demand. While on the supplier's side, they may find it hard to deliver sub-assemblies or a small quantity of parts. Womack and Jones, 1994. Lean production optimizes the skills of the workforce through encouraging continuous improvement activities, including integrating direct and indirect work and giving workers more than one task. Therefore, manufacturing a large variety of products can be carried out with lean production. Ireland and Dale, 2001, carried out a study on 3 different companies to determine the effectiveness of TPM implementation in real situations. It consisted of a UK plant with a wide range of rubber products, Company A, packaging company, Company B, and motorized vehicles manufacturing company, Company C. These were selected due to differences in their backgrounds such as number of employers, machinery used, organizational structure, and strategic objectives. The differences affected the TPM method of implementation in each company. Chan, E.T. A.L., 2005, studied an electronic manufacturing company to see whether TPM implementation is worth a move for any company. The general aim of this project was to know effectiveness and difficulties in TPM implementation. E.T. L., 2004, focused on how manufacturing industries in Nigeria can implement TPM by researching on their problems and shortcomings with the old traditional ways of maintenance. This way, the manufacturing industries can use this recommendation and suggestion as prerequisites before implementing TPM in their company. Friedley et al., 2010, recorded that a pharmaceutical manufacturing company increased their OEE from 36% in 2004 to 51% in 2009. In Friedley et al., 2010, case study, the main problem was the result of direct stoppage and breakdowns in the production. This unplanned maintenance work suggests that TPM implementation was not in its full potential, as the autonomous maintenance activity should reduce on this kind of losses. Daniel Ottoson, 2009, studied the initiation of TPM in a pilot line of German automobile company. The study showed remarkable improvements in OEE and the productivity per man-hour. 2 maintenance practices. There is an important goal in lean manufacturing practice, which is to become highly responsive to customer demand with the production of high-quality products. This goal has to be carried out in the most efficient and economical method, which are by reducing various waste in inventory, human effort, manufacturing space, and time to market. To make this happen, elimination of all kind of waste is essential. Waste exists in many forms and can be spotted at any place and in any time of operations. It does not add any value to the product. On the contrary, it will only consume the resources. Total productive maintenance is based on a combination of the concepts of productive maintenance, PM, maintenance prevention, MP, and maintainability improvement, MI. This shows where it's coming from and the direction it is supposed to take. It could be explained as being productive maintenance with the complete involvement of all parties. Nakajima, 1995. To understand the principle of TPM, a more detailed explanation is necessary. Nakajima uses 5 main points to explain TPM. The goal of TPM is the maximization of overall effectiveness. This serves the purpose of achieving machines running at their intended capacity without unplanned interruptions. TPM establishes a system for productive maintenance during the entire lifespan of the equipment. As reason would suggest, a machine tends to break down more towards its later days. Therefore, TPM aims to continuously keep machines in good shape and even facilitate maintenance. Also, TPM should be realized in all divisions of a company, so that engineering, maintenance, management divisions as well as the workers on the shop floor pull together. TPM is designed to promote productive maintenance through motivational management in minor, autonomous groups. A. TPM Principles. There are 5 major TPM principles. 1. Improving OEE by identifying possible losses of facilities and equipment, and monitoring all of them in case of speed losses, defect losses, and downtime losses. 2. Making frontline asset care as a part of the job. Frontline asset care, autonomous maintenance, is carried out by the operator, with support from the maintenance department. The operator should be able to fulfill at least some maintenance tasks, including simple repairs, preventive actions, and improvements, e.g. corrective actions, and proposing ways to prevent drawbacks to recur. 3. Having a systematic approach towards maintenance activities. This could be done by I. Defining preventive maintenance for each piece of equipment, time-based maintenance TPM. 2. Creating standards for running condition-based maintenance, CBM. 3. Defining maintenance responsibilities for operators and maintenance staff. Operators' responsibilities, general care. Maintenance staff responsibilities, general breakdown activities, supporting operators by training them, problem diagnosis, devising and assessing maintenance practice, developing maintenance actions and continuous upgrading of equipment. In order to thoroughly fulfill their duties and perform all their tasks, the employees need to receive continuous and appropriate training to develop their abilities like hand and operational skills, team working and problem solving. For early equipment management, zero maintenance is a concept inducing that failure causes and maintainability of the equipment should be considered during early stages of equipment lifespan like designing, manufacturing, installation and commissioning. Therefore, any problem can be tracked back and eliminated at the above-mentioned stages. Thomas R. Pomorsky, 2004, Immens BBBA, 2009. The principles allowing TPM to eliminate losses and maximize productivity are described in the TPM House, Fig. 1. It is based on the 8 pillars of TPM, defined by the Japan Institute of Plant Maintenance, JIPM Solutions Co., Limited, 2009. TPM 8 pillars. 5. Focused improvement, Kobesu Kaizen. This pillar states that small improvements are more effective than just one big improvement if they are continuous and encourage all employees to be involved. It aims to reduce losses that can lower efficiency. Kaizen is applicable in both production and administrative areas. Kaizen emphasis. I. Finding the ways of achieving zero loss in all activities. 2. Elimination of losses by means of using results of PM analysis widely. 3. Commitment toward cost reduction for resources. 4. OEE and OP improvements. Kaizen strives to make substantial improvements in productivity in forms of efficient equipment, operators, and material in addition to energy utilization. Kaizen tries to eliminate 6 losses, which are described below. V. Equipment failure, causes production downtime. By cooperation between the maintenance and production departments, equipment failures can be prevented by using predictive and preventive maintenance, developing operation practices and design changes. Root cause failure analysis. RCFA is a technique that is used after a failure occurrence. RCFA aims to eliminate failures and mitigate their impact. 6. Time for setup and adjustments. It includes the time for the warming up of a machine after its changing over. 7. Small stops. These stops last between 5 to 10 minutes and include minor adjustments and cleaning. 8. Speed losses. Several items may result in a machine working at a lower speed than what is determined before. These items can be no matching between machine and its application, inefficiency of the operator, unsuitable machine wear parts and substandard materials. 9. Losses during warming up. This includes losses in a quality point of view for products produced during the time of warming up. J. Venkatesh, ReliabilityWeb.com, 2009. B. Overall equipment effectiveness, OEE. Overall equipment effectiveness allows visualization of machine-related losses. This might seem easy at first, because with a machine theoretically able to run 24 hours a day and 365 days each year we get an amount of products representing the maximum capacity. Due to holidays and managerial decisions as not working on most weekends and so on, the maximum capacity is mostly never exploited, writes, 2008. Therefore, the quotient of the actual numbers of produced units put up against the maximum capacity yields the effectiveness of the equipment during the chosen time period, the overall equipment effectiveness, writes, 2008. It is important to keep in mind that the OEE is only a measurement of mechanical components. Therefore all losses, even those influenced by human aspects, such as changeovers, should be considered as the only interest in the OEE is to see whether the equipment runs according to its capability, writes, 2008. The basic requirement for a correct calculation of the OEE is precise data. All mechanical losses need to be recorded for best results. C. General model of OEE calculation. The formula for the calculation of OEE was developed by JIPM and is a factor from 3 different rates, namely availability, performance, and quality. Where ICT, ideal cycle time, is the quickest time at which the machine could produce a single part. PP, total parts produced inclusive of defective parts. Where GP, good parts produced. 3 methodologies for TPM-based focused breakdown reduction. A. Productivity model. The productivity model is defined in Fig. 2, capturing all machine parts, possible stops, responsibility and the owner of all stops. B. Model description. 1 total available time, TAT. This refers to the total clock hours available in a shift. For example, the day shift in company X runs from 0800 HRS to 1800 HRS, giving TAT of 10 hours, whereas night shift starts at 1800 HRS to 0800 HRS giving TAT of 14 hours. In this case the total available time is equivalent to total machine time, TMT, since there is no break between shifts. 2. Open time, OT. This is the total time available for production and is normally expressed as OT equals TMT planned losses. 3. Statutory time. This includes all gazetted holidays, planned offs and scheduled shutdowns. 4. Planned downtime. These are times planned into the production schedule, for example meetings, planned maintenance, machine cleanouts, breaks and trials. 5. Unplanned downtimes. These include breakdowns, short stops, external stops, like power outages, fire incidents, sick-offs and others, setup. Times necessitated by product change, speed losses, and quality losses. 6. Value added time. This time constitutes the total open time less planned and unplanned downtimes. C. Performance metrics. E. Standards developed. I. 1 point lessons. 2. Condition, inspection, and lubrication checklist. 3. Spare parts catalog. 4. Production log sheet. V. Skill gap analysis sheet. 4. Results and discussion. The results as discussed as follows. 1. OEE trends with time. From Figure 8 we can deduce that the OEE of WM Wrigley Company PK Line 6 is significantly increasing from 64.7% in October to 74.8% in February. The main contributor to OEE increase was the reduction in breakdowns and speed losses. The reduction in speed losses was attributed to the use of modular parts which ensured that the pulley running the drive was changed to match the original equipment manufacturer standards. Step 2 of master plan. The results herein agrees with the works of Friedli et al., 2010, point of departure being the focused breakdown reduction vis-a-vis total TPM implementation. 2. Variation of MTTR with time. The major contributors to the reduction in mean time to repair were I. The rearrangement of the spare parts store according to the movement of parts as well as cataloging parts per assembly greatly reduced the time spent by mechanics to find a part in the store, Fig. 6. 2. Development of 1-point lessons for standard setting of the major assemblies of the machine and tools to use assisted in ensuring a standard way of repair, Fig. 4. 3. Training of both mechanics and operators on machine standards. 4. The cleaning, inspection, and lubrication checklists assisted in noting possible breakdowns beforehand, hence allows for time to prepare to correct the problem. Which agrees with the works of Cameron Shahanagi, 2009. 3. Variation of mean time before failure, MTBF, with time. The mean time between failures initially reduced then increased from the third month onwards. The initial reduction was attributed to the restoration of basic machine conditions in step 1 and 2, Fig. 3. This is because during this period, the non-standard parts were removed and the original setting of the equipment restored. Lubrication, cleaning and inspection checklists had not been introduced into the system and many mechanics and operators had not been trained in the new standards. V. Conclusion. From the study, it was concluded that to develop an information system of the company, all intrinsic features of each machine are supposed to be well documented, including machine history with modifications if any are well collated and stored in the machine card. This was well covered under the early equipment maintenance pillar under the TPM pillars. Each of the assemblies and sub-assemblies are to be defined and well coded into the system. When calculating the performance metrics of a machine, a properly defined productivity model of the same must first be developed. The essence of this is that different machines have different loss types that have to be defined. This can be done through a time study at the shop floor. In reducing machine breakdowns, a proper systematic way of loss reduction has to be followed as described in Fig. 3. The strategy encompasses all aspects of the 4 Ms, man, machine, method, and material. When dealing with man, the strategy has training by utilizing a skill gap analysis, Fig. 12, for both mechanics and operators and defining standard operating procedures for the roles. Additionally, from the root cause analysis, 1-point lessons are developed to be used as training material. To reduce time wastage and spare parts management, and inventory of all parts was done, and the parts classified according to consumption. A parts catalog was developed, showing pictures for the most confusing parts with their bin numbers in the store, Fig. 6. Main outputs from the productivity model are standard reports. The reports from the data collected could be generated shiftly, daily, weekly, monthly, and yearly. The reports include OEE report, waste report, engineering loss report, breakdown recurrence report, team reports, and others. The variation of the report depends on the query sent to the database. The production of these reports aids in team management and encourages competition between teams.